Welcome to this deep dive into Apache Spark. Let's get started on mastering data frames. Welcome. Today, we are focusing on Spark data frames, which are the most important structured API in Apache Spark. Think of a data frame as a massive, distributed spreadsheet or a relational database table. It represents a distributed collection of data organized into named columns with an associated schema. The fundamental basics rely on two key concepts, partitions and immutability. Data within a data frame is physically divided into multiple partitions and distributed across your cluster's worker nodes, allowing parallel execution of tasks. Immutability simply means that once a data frame is created, you cannot change its data directly. Instead, any transformation you apply generates an entirely new data frame from the previous one. This design allows Spark to track operations safely, making it incredibly fast and fault-tolerant. By the end of this session, you'll be manipulating massive datasets with ease. Looking at our diagram, you can visualize how a Spark data frame manages data across a cluster. We start with raw data at the top, which is logically represented as a single Spark data frame. However, physically, Spark splits this data into multiple chunks called partitions. As you can see, partition 1, 2, and 3 are distributed and processed simultaneously across worker nodes 1, 2, and 3. This parallel processing is exactly how Spark handles petabytes of data at lightning speed. Because each core can work on a separate partition independently with different tasks, performance scales linearly with your cluster size. You might wonder, why do we prioritize data frames instead of the older resilient distributed datasets, or RDDs? The answer lies in two powerful internal engines, Catalyst and Tungsten. When you use data frames, Spark SQL's Catalyst Optimizer automatically optimizes your queries. It takes your high-level operations, like filters and joins, and transforms them into a highly efficient physical execution plan. Furthermore, data frames utilize Tungsten's efficient off-heap memory management and whole-stage code generation. This means Spark avoids the heavy overhead of Java object serialization and garbage collection. Ultimately, this automated optimization process results in significantly faster execution compared to manually writing and optimizing lower-level RDD operations. This flowchart illustrates the journey of your data frame code. You write high-level code using the data frame API, which is then fed directly into the Catalyst optimizer. Catalyst first generates a logical plan, applying strict optimization rules, such as predicate pushdown. It evaluates multiple physical plans, estimates their execution costs, and selects the most efficient one. Finally, the Tungsten execution engine takes this optimized physical plan and generates highly efficient Java bytecode for distributed execution. This is the hidden magic that makes data frame operations lightning fast without requiring you to manually optimize the underlying execution code. Let's talk about how you actually create a data frame. The starting point for all data frame functionality in modern Spark is the Spark session. Using the Spark session, you can easily load data from various file formats such as CSV, JSON, Parquet, or even traditional databases. To do this, you typically use the spark.read interface. For example, spark.read.json directly loads a JSON file into a data frame. When loading data, you have a crucial choice. You can either let Spark infer the schema automatically, or you can explicitly define it. While schema inference is great for quick exploration, it can cause performance bottlenecks on large datasets because Spark has to scan the data first to determine the data types. Our diagram shows the architecture of data ingestion in Spark. At the absolute core is the Spark session, the unified entry point for all data processing tasks. Through the Spark.read API, Spark provides a standardized way to connect to almost any data source. Whether your data resides in semi-structured JSON files, comma-separated CSVs, or highly optimized columnar Parquet files, the result is always exactly the same, a unified data frame object. This seamless integration means you can write the exact same transformation code regardless of where or how your underlying data is physically stored. Diving deeper into schemas, an explicit schema acts as the strict blueprint of your data frame. We build schemas programmatically using struct type and struct field classes. A struct type acts as a container for your entire schema, and inside it, you define multiple struct field objects. Each struct field defines the specific column name, its data type like string type or integer type, and whether it allows null values. Why go through this effort? Because explicitly defining your schema ensures that correct data types are assigned immediately and entirely eliminates the significant performance impact of Spark having to scan a massive dataset to infer the schema. It guarantees data integrity and dramatically reduces data loading times. This class diagram breaks down the specific components of a Spark schema. At the top level is the struct type object, which essentially represents the entire row structure of your data frame. The struct type is composed of an array of multiple struct field objects. Looking at the struct field class, you can see it requires three main properties: the string name of the column, the specific date type class, and a Boolean flag indicating if the column is nullable. By assembling these components programmatically, you give Spark a strict, type-safe contract for your data, bypassing the expensive schema inference phase entirely. Now that your data frame is loaded and strongly typed, you need to transform it. We use domain-specific language methods like select to choose specific columns and filter, or where, to restrict rows based on precise conditions. You can also add or modify columns seamlessly using with column. The most critical concept to grasp here is lazy evaluation. When you apply these transformations, Spark does not immediately process the data. Instead, it builds up a lineage of operations, a logical plan of what you want to achieve. The actual physical execution is deferred until you call an action, like show or count. This allows Spark to optimize the entire chain of transformations before reading a single row. This flow illustrates Spark's lazy evaluation model in action. We start with a base data frame and apply a filter transformation, resulting in a new, unmaterialized filtered data frame. We then apply a select transformation. At this point, absolutely no physical computation has occurred on the cluster. Spark has merely recorded our logical intent. It is only when we hit the final step triggering an action like show that Spark kicks into gear. It takes all the recorded transformations, optimizes them as a single cohesive execution plan, and then physically executes them across the distributed cluster. For high-level data summarization, data frames provide powerful aggregation methods. You will frequently use group by, paired with aggregate functions like count, sum, or average, to calculate business metrics across various categories. To maximize your processing performance, you must utilize Spark's built-in SQL functions instead of writing custom user-defined functions, or UDFs. Built-in functions process data in a highly optimized, columnar fashion and are fully understood by the Catalyst optimizer. Conversely, using UDFs forces Spark to serialize the data, process it row by row, and completely miss out on Catalyst's optimizations, severely degrading your job's execution performance. Always leverage the built-in functional API first. Let's examine how aggregations flow sequentially in a data frame. The initial data frame flows into a group by transformation, where the data is logically partitioned by a specific category, such as department. From there, we pass it through the ag method using Spark's highly optimized built-in functions. Here, we compute multiple metrics simultaneously, like the sum of salary and the average of age. Because we use built-in functions, Spark can perform these calculations directly on the Tungsten engine's optimized data layout, merging the results rapidly into the final aggregated data frame without the severe serialization overhead of UDFs. To truly master data frames as a senior engineer, you must learn to read query plans. By calling the explain method on a data frame, you can inspect the exact physical execution plan Spark intends to run. This is your ultimate roadmap for debugging. It reveals the parsed, analyzed, optimized, and physical plans. When optimizing, your primary goal is to minimize shuffle operations. Shuffles occur when data needs to be redistributed across the cluster, such as during a heavy join or a group by operation, and they are extremely expensive. A critical technique is early filtering. Always filter out irrelevant rows before grouping or joining to drastically reduce the volume of data being shuffled across your network. This diagram maps out the diagnostic pipeline when you invoke the explain method. Spark outputs a comprehensive multi-stage plan. It begins with the parsed logical plan, moves to the analyzed logical plan where column schemas are resolved, and then passes through the Catalyst optimized logical plan. Finally, it produces the physical plan, which is the actual execution blueprint. As an expert, your eyes should go straight to the bottom of the physical plan to look for exchange nodes. These specific nodes indicate data shuffles. Identifying and minimizing these exchanges through techniques like early filtering is the master key to tuning your Spark jobs. Let's tie this all together with a highly important real-world use case: processing massive e-commerce sales logs. Imagine ingesting terabytes of daily JSON transactions. First, we define an explicit struct type schema to avoid scanning overhead and guarantee data integrity. We load the JSON using this exact schema. Next, we implement early filtering, immediately stripping out failed or null transactions before they cause shuffle overhead. Then, we use built-in functions to group by the region and aggregate total revenue. Finally, we write the aggregated data frame back to storage in a highly compressed, columnar format like Parquet. This end-to-end pipeline is fault-tolerant and production-ready. Please like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Take a look at our final production pipeline diagram. We ingest the raw JSON sales logs while enforcing an explicit schema right at the data source. The data flows into our data frame, where we immediately apply an early filter to strip out unwanted records, vastly reducing the overall data volume. The clean data then enters the aggregation phase using high-performance built-in functions rather than slow UDFs. Finally, the highly summarized, valuable business data is written out to Parquet files, perfectly optimized for downstream analytics. By following these strict principles, you ensure maximum efficiency in Spark. Thank you for joining this training session.